machine. Okay, there are a lot of friends to study using this kind of stagnation point flow to study as a basic flow. Okay, without any reaction to know how the shear of this flow, and this shear also influence your combustion efficiency. Okay, so this is without any reaction, we know the exact solution for this. So we know every point in the velocity shear. Okay, and based on the shear and with the combustion even more complicated, right? So we have the velocity with the shear, so we know where is combustion can take place due to the shear, or where is cannot. Okay, because of velocity shear, velocity gradient. Okay, and that will be influence a lot of combustion detailed information about reaction flow. And reaction flow mean we have if you study this kind of flow with combustion, you measure the concentration for each reactant. 你去量测每一个反应气体的浓度的话 ，okay, because of this shear, you get a very beautiful distribution according to the shear. Okay, and then this shear also influence because when you have a shear, sometimes some place your combustion efficiency is not so high, so your concentration will be increased at that location. When you have a better combustion efficiency, all the reactant gas has a combustion reaction, and after combustion reaction, only the product's concentration will be raised up. Okay, so you have all kind of this kind of study based on this kind of flow pattern to study the stagnation point flow, and then as an example case, and try to understand all this mechanism of the reaction flow. Okay, 所以我们常利用这个当做一个标准的一个流场来用来做研究什么？研究这些 combustion reaction 的一些流场加上化学反应在这里面的时候，它化学反应会怎么样 ？OK， 而且就随着位置的改变而改变，这跟流场都有关系。OK， 所以 So this is very basic example for a lot of the physics inside this stagnation point flow. Okay, and here, this is another name for this flow, the Hint mass flow. Okay, this is so I already mentioned our stagnation flow can be approximated as a stagnation flow for a curved surface. As you can see, curved surface already erased, right? When you have a curved surface near the region here, near the stagnation region here, we always can assume this is the flow, is a flat plate, and then this is flow is normal to a flat plate. So the radius of curvature is much greater than the size of region. If this size of region with the radius of the curvature, okay, we always can study locally the flow, okay, for this. Okay, and for this flow, as you can see, we have a non-linear turn here. Okay, and I can show you here is a later I can show you this non-linear turn. Okay, in the Navier-Stokes equation. Okay, and how to solve this flow? What to solve this flow? How to solve the exact solution for this flow? The exact solution for this flow is we will not directly solve this flow directly. Instead of directly solve this, we using the previous, if you remember in the chapter 4, we have a potential flow, right? Potential flow, we start this also a corner flow. As you remember, we have a flow like this, flow pattern. Okay, this is the corner flow, right? It's a right angle corner flow. Okay, and the right angle corner flow, our pressure, our compressed potential is equal to 1. Right? If you have uniform flow here, U is uniform downward. And if a corner here, okay, this flow pattern can be written as compressed potential is UZ to the 1 half order. Okay? So this flow here, we can have this kind of physical sense. Outside this near wall region here, okay, So outside the near wall region here, since near wall region we have a very viscous effect near the boundary here. Okay, but outside this boundary layer region or the near wall region here, outside here, okay, can we assume is a so-called potential flow? Okay, so we can assume outside region here we have implicit incompressible rotation. That means the potential flow. Okay, solution flow. Okay, but near the boundary layer region or near the wall region here, because the wall I mentioned is there's a viscous effect, right? And viscous effect start to dominate. So near wall region here, we have a viscous within the boundary layer, and viscous within the boundary layer is our carbon equation, Navier-Stokes equation with a constant viscosity. Okay, and as you can see, I neglect this term because this term is what is unsteady term. For this flow is a steady, okay, steady state flow. Okay, we don't have any unsteady. So this is nonlinear term. This is nonlinear term here. Okay, and we have a pressure gradient and we have viscous term here. Okay, so our carbon equation outside the boundary layer, we assume is a potential flow. This is the carbon equation. Near the wall region, we can modify to what? This Navier-Stokes equation. Okay. So that's this point. We modify our potential. We know the solution here. Okay, because we already from the chapter 4 we have this solution form outside this boundary here. So from the potential flow solution that can represent outside region here, the solution here, and this region here, the flow. Can I modify this solution? Can I modify this solution to satisfy the non-state boundary condition on the wall? Okay, because the only difference for this and this is what? For this Navier-Stokes equation, because we have viscous term here, so we satisfy the non-state boundary condition. But the potential flow is what? Potential flow don't have this kind of boundary condition. Potential flow, the boundary condition. What's the potential flow boundary condition? No flow close to the boundary, right? But the flow can parallel to the boundary, tangential to the boundary. There's a flow. However, no flow close to the boundary. That means this is the wall, this is boundary. Normal direction of the velocity normal to the wall is equal to 0. However, tangential velocity is not equal to 0. That's a potential flow. Okay. And for the viscous flow, what? Both normal and tangential velocity are equal to 0. That's represent a non-state boundary condition. Okay, so one possibility here, one thinking is can we modify our solution from the potential flow, and that can be satisfied our non-state boundary condition and also the Navier-Stokes equation here. Okay, Navier-Stokes equation here. So that's a kind of thinking we try to do, okay, to solve this problem. Okay, let's start to thinking. Potential flow. Okay, you learned that before in chapter 4. We just finished chapter 4. So the potential flow in the sector angle pi over 2, we have this complete potential. Okay, Fz is uz squared. Right? So that represents the potential flow for a stagnation point flow. Okay, and then we take a derivative df dz and give you the complex velocity. Complex velocity for this is what? 2uz, and 2uz is equal to u minus iv, right? You have to remember this is minus sign here. So here we can have a u is equal to 2ux, v is equal to minus 2u1. Okay, that's a potential flow solution, right? So that's a potential flow solution. And then remember, in the potential flow, we always come with what? Come with the Bernoulli equation. And Bernoulli equation, this is our pressure at any location x, y. This is our stagnation pressure, okay? Stagnation pressure, that means velocity equal to 0 point, we call it stagnation point. And this stagnation point, we have a pressure reduced to P sub 0. And so P sub 0 minus 2 rho u squared give you the pressure for any location for a potential flow. Okay, that's a Bernoulli equation. Okay. So this is the one. This solution form represent what? Represent only the outer part of this here. Okay, the part. So let's talking about the near wall region here. We should consider the non-slip boundary condition due to this viscous turn here. So the Navier-Stokes equation. Okay, this is Navier-Stokes equation. The different from the the potential equation. Remember, potential equation is what? It's also from. If you neglect this term here, what's this equation? You got the Euler equation, right? And Euler equation is only this term drop, right? And this term drop is can represent incompressible, invisible flow. And only one additional irrotational can reduce potential flow, right? So compare with the potential flow solution with the Navier-Stokes equation only this term here, because this term here incompressible, invisible, incompressible, this term will be dropped, right? So only additional term for the Navier-Stokes equation, viscous term is as you can see this term here, Laplace V, okay, and here Laplace V, this is one additional term. Okay, this additional term is the only difference between the potential flow and what? And Navier-Stokes equation, viscous flow. And as you can see, V in the potential flow can be represented as a so-called gradient phi, right? This is the velocity potential. And you can switch these two operators. Okay, if you switch this and this, become like this. As you can see, this is Laplace phi, and this take a gradient. Okay, we just switch this operator and this operator. And what's Laplace phi? Laplace phi should be equal to 0, right? Laplace phi for potential flow. So as you can see, potential flow solution, if you using the potential flow solution into this viscous term here, this should be also equal to 0. That means what? The solution form, okay, solution form for the potential flow is also the solution form for the Navier-Stokes equation. Equation is the same, but only is what? Different is what? Boundary condition is different. Solution is the same form, because if you compare this and this, right? Only the difference is this term. And this term also, if you're using the V is equal to gradient phi, this term also equal to 0. Make no difference. So Gaussian equation no different. What? Only different is what? It's a boundary condition. This boundary condition for the potential flow, only the normal to the wall is equal to 0. However, for the near wall region here, we should satisfy what? We should satisfy non-slip boundary condition. Both U and V is equal to 0. Okay, so you can see so we only the difference is the non-slip boundary condition. Different. So what should we do is what? By modify the potential flow solution to what? To satisfy the non-slip boundary condition near the wall. Okay, that will be our job to do, right? We can. And how can we do that? Because near the wall region is a function of y here, right? This is y is a smaller region because this is the coordinate. This is x. This is y. So when y is small near the wall here, so we should change our solution form near the y only. But when the y is large, okay, that's within this region, we don't have to change our solution form. So what we did is we modify our solution form. U is equal to 2ux, right? And this 2ux is from the potential flow solution. And we change slightly what? We change this u become 2us times a function of y. Okay, and this we use the f prime y, okay, as this function. And this function is what? We're using this function to satisfy our non-slip boundary condition. Okay, we say that non-slip boundary condition. Okay, and let's do that. Okay, so this is u velocity. Should modify from the potential flow and become u equal to 2ux f prime y. Okay. So this is our case. Okay, solution form. If I can change the solution form to this, okay, and also satisfy the non-slip boundary condition, I may be able to find a solution for this Lagrangian point flow solution. Okay, so that's physics. Okay, try to do that. So we try to using this as solution form and try to plug into the continuous equation first. And continuous equation give you a partial u partial x plus partial b partial y equal to 0, right? So partial b partial y equal to minus partial u partial x. U is this form here, and partial u partial x, this is x here, becomes 2u f prime y here. So partial b partial y equal to this, and you take a what? You take the integral of y, give you the v velocity. So you integrate once, give you what? V is equal to minus 2u, because this f prime is a derivative with y, and once you integration with y, become f prime y is equal to fy. So that's the purpose why we're using f prime here. Okay, because we would like to do the integration here and find out this. Okay, here we don't want to use in the integration form. Okay, for the solution form. So we have a u like this. Okay, we can modify our u like this and modify our v should like this. Okay, so from the potential flow we modify u, and from the plug into the continuous equation we should know the v velocity should look like this. And then we can discuss, okay, like this. This is a u, right? This is a v, okay. This is discussed. So we should, by changing, the purpose of changing this and here is what? At the y equal to 0, we should satisfy our non-state boundary condition, right? That's the main purpose. Okay? So at the y equal to 0, u is equal to 2ux f prime y equal to 0 is equal to 0. Okay, you should copy this if you want. Okay, but okay, that gives you us what? F prime y equal to 0 is equal to 0, right? That's one of the boundary conditions for this f function should satisfy. Okay, if you want to satisfy a non-state boundary condition. What's a v? V is this function, right? Once we modify, okay, using the continuous equation to modify. So this is u, v is equal to, when y equal to 0, f y equal to 0 should be equal to 0 because of the non-state boundary condition again. Right? So our f y equal to 0 should be equal to 0, right? Because of this. This is a constant. Okay? So this is a two bound. For f function, we have the y equal to 0. Both of the y equal to 0 for f and f prime should be equal to 0. Okay? And another one, okay? As you can see here, our outer flow is what? It's a potential flow. Our solution form should look like our velocity and pressure field out of region should like this, right? In the near the wall region, I using this, okay, and try to find out our solution form. So near the region, the flow, our solution form I already modified like this, okay? And this modify the solution form also have to satisfy what? When y approach to infinity, what happened? When y approach to infinity, like here, what happened? This solution form should go back to what? Should go back to potential flow solution. 对，这个流场，我们刚刚虽然这个地方假设成这样子，去符合这个地方的流场，可是这个地方的流场，它当它 y 趋近于无穷大的时候，应该它要跟外界的 solution 叫 match。Okay, so y go to infinity, our u velocity, this is u, y go to infinity, should approach to what? Approach to solution for potential flow. U is 2ux here, 2ux here. Y, v is what? V is minus 2uy here when y go to infinity. So we have two additional, okay, boundary conditions for f function, f prime infinity and f infinity. F prime infinity is equal to what? Should be equal to 1, because this is equal to 1, 2ux, 2ux. And f infinity should be equal to what? F infinity should be equal to y. Right? This f infinity should be equal to 1. Okay? So finally we have this, okay, f y equal to 0, f prime y equal to 0, f equal y equal to infinity, f prime y equal to infinity. We have, so this f function should satisfy this. Okay, all these boundary condition. Okay, so this is so we go back to our lecture note. Okay, our lecture note is we modify this, and then this is from the non-state boundary condition. We have this and equal to 0. We already. So once you assume that if you can match this, our non-state boundary condition can satisfy. Okay, when y go to infinity, okay, you should be matching with a potential flow solution. Okay, outer potential flow solution. So we have f equal to y, okay, and f prime equal to 1. You say this f prime equal to 1 here. Okay, can you follow me? 可以吗？我都没有注意到这边的反应。同学在笑，到底懂还不懂 ？OK， 你应该把它抄下来，或者是，因为今天想要把它讲清楚一点，因为以前都是直接这样讲，你们大概不知道到底在讲什么。这边只是更清楚。Okay, so once you have that, okay, once you understand this point, we should continue our discussion, right? So our discussion here, so we have this is our x momentum equation, we have a y momentum equation. And this is our solution form, okay? U is equal to 2us f prime y, v is equal to 2uf. This is our boundary condition. This is our 4 boundary condition, actually. Okay, this is our 4 boundary condition. Okay, so what's next? We try to using this solution form into this momentum equation, right? And then try to derive the carbon equation for the f function. Okay, that's it. This by using the first x momentum equation. This is x. So u. This is u, right? And partial u, partial you can take a derivative of partial u, partial u. V is this. Partial u, partial y is become f double prime y, right? And this is the pressure gradient we just keep. And this is the second order partial square u, partial x. You can take second. So this should be equal to 0, I believe, right? Because the x and another x should be equal to 0. That should be cancelled. And then f squared y become a triple derivative, right? Triple prime. Okay, here. So as you can see here, we plug each term here, it becomes like this. This is triple, okay, f triple prime here. I just mentioned this term should be dropped. And this is a pressure term here. And this term just u times partial u, partial y give you this term. And this is u times partial u, partial x give you this term. Okay? Second, y momentum equation. And why do you want to use this? Because this is 2-dimensional flow. Yeah. As you can see, this is 2-dimensional flow. Our flow is changeable with x and y. So we should using the both direction. We should using the x momentum and y momentum equation. This is 2-dimensional flow. And then u again, similar with using this solution form into this y momentum equation can be reduced to this. Okay, and we can start from the y momentum equation because y momentum equation we don't have any x function. This is a y function because f is only function of y. F prime is function of y. This is a y integration. So we don't have any x variable here. So we can directly integrate the pressure partial p partial x, integrate this solution with y direction, right? Integration with a y. So we integrate, okay? Along the y we get the p pressure field. So if we integrate this, become what? Become this term here, okay? This term here. You integrate this. If you integrate this, become this term here. Okay, because 2 mu u f double prime and integrate with y become f double prime become f prime only, right? That's it. When you integrate, you always introduce what? Integration constant. 你有积分就有个积分常数，对不对 ？Okay, so integration constant is function of x, right? It's a function of x because we integrate with y. Okay, integration constant should be a function of x. Okay, because we keep x as a constant. Okay, so this is the pressure field by integration with Y momentum equation. And what's from this equation? We should do that. What? Pressure field, remember, outer region, we know the pressure field look like. This is from the potential solution. Right? So that means Y approach to infinity. The solution form part, the pressure field should be approached to this solution form, right? Because so that's when Y go to infinity, this F is equal to what? When Y go to infinity, F is equal to what? Y equal to infinity, F is equal to Y here. Okay, so all this F squared become Y squared. Yeah. Okay, and F prime, what happened to F prime? F prime Y go to infinity should be equal to 1. So this is equal to 1. So this term reduced to this term here. Okay? And this solution form should be equal to what? Should be equal to our potential flow from the solution, pressure field solution from potential flow. So these two should be equal. Okay? These two should be equal. Okay, if you do that, you can find out your Gx. Okay, this equal to this, and then find out your Gx. Okay, find out your Gx. Okay, so Gx is equal to this, because as you can see here, this term and this term, 2 log U squared Y squared is cancelled, right? And then become P sub 0, and then minus this term here, 2 log U squared S squared, and plus this term here, 2 mu U equal to your Gx. So our integration constant Gx should be equal to this. If I set our integration constant Gx equal to this, our pressure field can satisfy the potential flow when Y go to infinity. Right. Okay. Finally, I can write down. I plug into this integration constant into here, and then try to rewrite our pressure field like this. Okay. So this is a pressure field look like. Okay. And this pressure field, by applying this boundary condition, we can satisfy the pressure field can match to the outer solution. That means the outer potential flow solution of pressure field. Okay, so this is the pressure field look like. Okay, if I written our pressure field look like this, I can satisfy the outer field. Okay, outer potential flow solution, pressure solution. Okay, so this is the pressure, and then so the next we try to using this X momentum equation, because we already used this to find out our pressure field. And this term here, partial P, partial X. So we have a pressure term like this. So partial P, partial X. So partial P, partial X is only this term. This is constant, so this is cancelled. This is a Y function, so this is cancelled. This is also the Y function is cancelled. So only this term here. So minus 4 log U squared X. Okay, so I plug this partial P, partial X into this X momentum equation here and try to rewrite this equation. This equation looks like this. Okay, this equation. So this is X momentum equation by using the pressure field we just derived, and this is the pressure field, partial P, partial X. And then we rearrange this equation. This equation become F triple prime. Okay. So this is still, what's this? This is Olden differential equation, right? But third order, right? 三阶的. Okay. So we can simplify our carbon equation. Try to find out this solution form with F triple prime. Okay. This carbon equation with the rest of the 3 boundary condition. These 3 boundary, this and this and this here, and we can solve this solution. Okay. Can we use in the handwriting? Okay. So this is well-posed mathematical problem. Try to solve this function of fy. Okay.